In Part 6 of Lecture 2, we will discuss memory management, information security, and resource management. The needs of users can be met best by a computing environment that supports modular programming and the flexible use of data. System managers need efficient and orderly control of storage allocation. The operating system, to satisfy these requirements, has 5 principal storage management responsibilities. Process isolation. The operating system must prevent independent processes from interfering with each other's memory, both data and instructions. Automatic allocation and management. Programs can be dynamically allocated across the memory hierarchy as required. Allocation should be transparent to the programmer. Thus, the programmer is relieved of concerns relating to memory limitations, and the operating system can achieve efficiency by assigning memory to jobs only as needed. Support of modular programming. Programmers should be able to define program modules and to create, destroy, and alter the size of modules dynamically. Typically, operating systems meet these requirements with virtual memory and file system facilities. The file system implements a long-term store with information stored in named objects called files. The file is a convenient concept for the programmer and is a useful unit of access control and protection for the operating system. Virtual memory is a facility that allows programs to address memory from a logical point of view, without regard to the amount of main memory physically available. Virtual memory was conceived to meet the requirement of having multiple user jobs reside in main memory concurrently, so there would not be a hiatus between the execution of successive processes, while one process was written out to secondary storage, and the successor process was read in. Because processes vary in size, if the processor switches among a number of processes, it is difficult to pack them compactly into main memory. Paging systems were introduced, which allow processes to be comprised of a number of fixed-size blocks called pages. A memory references a word by means of a virtual address consisting of a page number and an offset within the page. Each page of a process may be located anywhere in main memory. The paging system provides for a dynamic mapping between the virtual address used in the program and a real address or physical address in main memory. With dynamic mapping hardware available, the logical next step was to eliminate the requirement that all pages of a process reside in main memory simultaneously. All the pages of a process are maintained on disk. When a process is executing, some of its pages are in main memory. If reference is made to a page that is not in main memory, the memory management hardware detects this and arranges for the missing page to be loaded. Such a scheme is referred to as virtual memory and is depicted in the figure on the slide. The processor hardware, together with the operating system, provides the user with a virtual processor that has access to a virtual memory. This memory may be a linear address space or a collection of segments, which are variable length blocks of contiguous addresses. In either case, programming language instructions can reference program and data locations in the virtual memory area. Process isolation can be achieved by giving each process a unique, non-overlapping virtual memory. Memory sharing can be achieved by overlapping portions of 2 virtual memory spaces. Files are maintained in a long-term store. Files and portions of files may be copied into the virtual memory for manipulation by programs. The figure highlights the addressing concerns in a virtual memory scheme. Storage consists of main memory that is directly addressable by machine instructions, and lower speed auxiliary memory that is accessed indirectly by loading blocks into main memory. Address translation hardware, or memory management unit, is interposed between the processor and memory. Programs reference locations using virtual addresses, which are mapped into real main memory addresses. If a reference is made to a virtual address not in real memory, then a portion of the contents of real memory is swapped out to auxiliary memory, and the desired block of data is swapped in. During this activity, the process that generated the address reference must be suspended. The operating system designer needs to develop an address translation mechanism that generates little overhead and a storage allocation policy that minimizes the traffic between memory levels. The growth in the use of time-sharing systems, and more recently computer networks, has brought with it a growth in concern for the protection of information. The nature of the threat that concerns an organization will vary greatly depending on the circumstances. However, there are some general-purpose tools that can be built into computers and operating systems that support a variety of protection and security mechanisms. In general, we are concerned with the problem of controlling access to computer systems and the information stored in them. Much of the work in security and protection as it relates to operating systems can be roughly grouped into 4 categories. Availability, concerned with protecting the system against interruption. Confidentiality, assures that users cannot read data for which access is unauthorized. Data integrity, protection of data from unauthorized modification. Authenticity, concerned with the proper verification of the identity of users and the validity of messages or data. A key responsibility of the operating system is to manage the various resources available to it, namely main memory space, input-output devices, and processors, and then to schedule their use by the various active processes. Any resource allocation and scheduling policy must consider 3 factors. Fairness. Typically, we would like all processes that are competing for the use of a particular resource to be given approximately equal and fair access to that resource. That is especially so for jobs of the same class, that is, jobs of similar demands. Differential responsiveness. On the other hand, the operating system may need to discriminate among different classes of jobs with different service requirements. The operating system should attempt to make allocation and scheduling decisions to meet the total set of requirements. The operating system should also make these decisions dynamically. For example, if a process is waiting for use of an input-output device, the operating system may wish to schedule that process for execution as soon as possible. The process can then immediately use the device and then release it for later demands from other processes. Efficiency. The operating system should attempt to maximize throughput, minimize response time, and in the case of time sharing, accommodate as many users as possible. These criteria conflict. Finding the right balance for a particular situation is an ongoing problem for operating systems research. Scheduling and resource management are essentially operations research problems, and the mathematical results of that discipline can be applied. In addition, measurement of system activity is important to be able to monitor performance and make adjustments. The figure on this slide suggests the major elements of the operating system involved in the scheduling of processes and the allocation of resources in a multi-programming environment. The operating system maintains a number of queues, each of which is simply a list of processes waiting for some resource. The short-term queue consists of processes that are in main memory, or at least an essential minimum portion of each is in main memory, and they are ready to run as soon as the processor is made available. Any one of these processes could use the processor next. It is up to the short-term scheduler or dispatcher to pick one. A common strategy is to give each process in the queue some time in turn. This is referred to as a round-robin technique. In effect, the round-robin technique employs a circular queue. Another strategy is to assign priority levels to the various processes, with the scheduler selecting processes in priority order. The long-term queue is a list of new jobs waiting to use the processor. The operating system adds jobs to the system by transferring a process from the long-term queue to the short-term queue. At that time, a portion of main memory must be allocated to the incoming process. Thus, the operating system must be sure that it does not overcommit memory or processing time by admitting too many processes to the system. There is an I/O queue for each I/O device. More than one process may request the use of the same I/O device. All processes waiting to use each device are lined up in that device's queue. Again, the operating system must determine which process to assign to an available I/O device. The operating system receives control of the processor at the interrupt handler if an interrupt occurs. A process may specifically invoke some operating system service, such as an input-output device handler, by means of a service call. In this case, a service call handler is the entry point into the operating system. In any case, once the interrupt or service call is handled, the short-term scheduler is invoked to pick a process for execution. The foregoing is a functional description. Details and modular design of this portion of the operating system will differ in various systems. Much of the research and development effort in operating systems has been directed at picking algorithms and data structures for this function that provides fairness, differential responsiveness, and efficiency.